Hello and welcome to this session. I am Marco Ip. I would like to share the Groundborne noise reduction by real damper effect on P2 resonance. In this presentation, I will talk about Groundborne noise mitigation and retrofit solution. Then we will talk about the relationship between Groundborne noise and P2 resonance. Last year, we have a breakthrough in the real damper technology, such that the real damper is strong enough to reduce low-frequency real vibration and the associated Groundborne noise. Then I will share the laboratory test results. And finally, I will talk about the potential impact to the real industry and the EIA process. Let's start with the current Groundborne noise mitigation practice in the industry. Here are the vibration isolation track forms that may be retrofitted, including high resilient base plate, such as the Delca 8 Pendule Flanger. Although it is practically feasible to be retrofitted, this retrofit solution takes an enormous amount of time and it is rarely seen in the industry. Here we have the low vibration track form LVT and the floating slab track FST. By all means, they are not able to be retrofitted. FST needs to be planned a few years before the railway line operation due to their extra limitations on tunnel space and faulted loading. The currently available retrofit solutions are to replace the track form with high resilient base plate, which is time consuming, or to slow down the train speed, which increases the journey time. Both of them are not a favorable solution. Now, we come to the mechanism of Groundborne noise and P2 resonance. P2 resonance is a simple harmonic motion of the combined mass of real and real. The combined mass of real and real is sometimes called unspring mass. The P2 resonance frequency is controlled by the base plate stiffness and the unsprung mass. Generally, the frequency range is around 30 to 100 Hz for stiffness 10 to 100 kN per millimeter. Here is a simple model for the P2 resonance, which may also be called as unsprung mass resonance. I am sure that it may recall you the natural frequency equation for the simple spring mass system. P2 resonance is controlled by the base plate, stiffness, and unsprung mass. Another vibration source is the fastener passing vibration. It is created by the regular spacing between the fasteners. For metro train speed between 70 to 110 kph, the fastener passing frequency will be around 30 to 50 Hz. When the fastener passing vibration coincident with the P2 resonance frequency, the Groundborne noise issue will be exaggerated. On top of the P2 resonance and fastener passing vibration, soil mobility also plays a critical role in Groundborne noise problem. Soil mobility generally peaks at frequency below 100 Hz. If the soil mobility peak frequency is close to the P2 resonance frequency, then the Groundborne noise will become serious. Last year, we have a breakthrough in damper technology. The breakthrough included 4 major concepts: in-phase oscillators pair, independent tunable frequencies for vertical and lateral vibration, retrofit rigid mounting to allow coupling of extra high damping force, and modular design allows multiple dampers installed in single spacing or half installation. We have tested 2 types of dampers: Type A with independent oscillators, and Type B with in-phase oscillators. We observed that the damping force provided by Type B increased by around 30 to 40%, and we believe it is benefited by avoiding the destructive interference between 2 adjacent oscillators. Although all the oscillators are tuned to be identical frequency, the slightly difference in the rubber properties would result in a slight difference in the oscillation frequencies. In the independent oscillators, periodic destructive cancellation is inevitable as shown in the animation. Such as destructive cancellation would not be occurred in the in-phase oscillators pair. With our latest design, the oscillating frequency can be independently tunable along the vertical and lateral directions. The modular design allows a quick and rigid installation. It also maximizes the oscillator mass ratio. Further, it allows flexible installation pattern to suit whatever needs according to the site situation, which includes quarter installation, half installation, single installation, double installation, and triple installation. Now comes the interesting part. We will cover the testing setup and the result in the coming slides. We have a 500 kg steel block sitting on the top of the rail to simulate the mass of a wheel. A shaker providing a broadband excitation directly connected to the steel block. Then the P2 resonance appears naturally. In this setup, the P2 resonance is around 47 Hz. Dampers can be installed along the rail. Here is the photos of the experimental setups. Without damper, 2 dampers and 6 dampers are installed. Here is a diagram for the test setup. Test 1 is to establish a baseline for the untreated rail vibration. Test 2, Test 3, Test 4, and Test 5 are to investigate the effective length which the dampers are able to suppress the P2 resonance within the effective length. In Test 6, 6 sets of dampers are placed close to the wheel set. Here are some photos of the test setup. The yellow circle indicates the accelerometer placement. Gap filler were used to short-circuit the oscillators in order to study the tuned mass damping effect. The black lines are the rail and floor vibration without damper installed. These light blue lines are the vibrations with 2 dampers installed under the rail, but with gap fillers to short-circuit the oscillators. The blue lines are the vibration after removing the gap fillers. We can see that the effect of the oscillators are critical. Here is the result presented in the paper. Around 5 dB reduction was achieved as the P2 resonance frequency in both the rail and floor vibration. A peak around 35 Hz appears owing to the floor structural resonance, excited by the adjacent activities within the building. After we submit the paper, we dig further to increase the shaker force. With a band pass filter, we are able to raise the shaker force output by around 10 dB. The following slides will present the latest testing results after the paper submission with the improved signal-to-noise ratio. First, we have the black lines showing the P2 resonance around 47 Hz at both rail and floor. We then install the dampers, the Type A independent oscillators, tuned at 47 Hz, at spacing far away from the wheel set. The green line shows the vibration level with damper installed 1 spacing away. The reduction becomes significant at the P2 resonance. The blue line with dampers installed in the middle spacing shows an even better vibration reduction. With 6 dampers installed within the effective length, more than 10 dB reduction was achieved at the tuning frequency. We conducted for the same test for Type B in-phase oscillators. Similar to the previous testing, when it is far away from the source, the damper shows no effect. However, when the dampers are installed within the effective length, it provides a larger reduction than the Type A independent oscillators. With 6 dampers installed within the effective length, the reduction is around 13 dB at the tuning frequency. When we look at the peaks at different frequencies, the vibration reduction is only 6.4 dB on the floor, even with 6 dampers installed. it is already a remarkable breakthrough. Then we tune the oscillators at frequency covering the adjacent peaks. In each spacing, we have 4 oscillator pairs, 2 of them tuned to 47 Hz, 1 to 41, and 1 to 52. The peak-to-peak vibration reduction is improved to 8.9 dB. The potential impacts to the railway industry and the EIA process. With another year development in Groundborne noise rail dampers, Groundborne noise retrofit solution for 5 to 8 dBA reduction can be achieved. No need to slow down train speed for reduction of Groundborne noise, because the damper vibration reduction is better than half the train speed, and without impacting the journey time. EIA safety factor on top of the worst case scenario can be reduced or totally removed. Saving FST construction costs by minimizing the use of FST. Saving tunnel construction costs because of the smaller tunnel size without FST. Groundborne noise target can be adjusted according to the local's complaint. Way shorter planning than the FST, which requires years of planning. Thank you for joining our session.